Hello students, this is Mr. Allen, and today we're going to look at section 8.4, which is on the comparison tests. As we're moving through chapter 8 here, you're going to see that the next few sections, we're just going to keep revisiting more tests. So in the last lesson, I think we looked at the P-series test and the integral test to determine whether a series converges or diverges. Today we're going to look at two more. We are going to look at the direct comparison test to determine if a series converges or diverges, and something called the limit comparison test. And I'm going to try to do some examples of each of those. So let's start off with the direct comparison test. For a convergence test, the terms of the series have to be fairly simple, and the series must have special characteristics for us to use convergence tests to be applied. So that's kind of the challenges. Once we're through all this material, you guys got to figure out which test to use. A slight deviation from these special characteristics can make a test non-applicable, and that's what we're going to see. Here's some examples. So, for example, consider this series, this geometric series, the series 1 over 2 to the n. That's geometric, so we can use the fact that r is 1/2 there to determine that it converges. However, if I gave you a slightly different series, where it's n over 2 to the n, you cannot apply the geometric series test to determine if that converges or diverges. In number 2, here we clearly have a p-series with a p-value of 3. But if you look at this series, by the way, we can then determine if that converges or diverges using the p-series test. You cannot apply it in this case, though, because that is not a p-series. And the third example here, if a sub n was this formula, n over n squared plus 3 squared, we can integrate that pretty easily using u sub. However, it's not so straightforward when I gave you a different b sub n based on that formula. Let's look at the direct comparison test. Here's what it says. We're basically going to directly compare two series. But here's the key. This is the most important part of what we're going to say right here. We're going to assume that, first of all, they're all positive, and that the a sub n is less than b sub n. So in other words, let's say the b sub n's, I'll do these in red. So let's say these are the b sub n's, that's b sub n. We need the a sub n's, which I'll do in green. We need our a sub n's to be below, less than or equal to, and I'm going to make them all less than in this case. So the green is the a sub n. So notice that the a sub n is less than the b sub n and everything is positive. So if the top series, b sub n, if that guy converges, then that's going to force the a sub n, which is below it, to converge. And that kind of, I think, is intuitive. Similarly, but in a different way, if the bottom series, that's the a sub n series, if it diverges, then the b sub n is going to diverge. So if the bottom series goes off to infinity, and we know all the terms in b sub n are greater than it, then it also has to diverge. Let's look at an example. It says determine the convergence or divergence of this series. So we've got the sum of 1 over 2 plus 3 to the n. Well, if we look at that, if you look at the a sub n, if you will, it looks a lot like the 1 over 3 to the n, which is a geometric series, and it is convergent. And I'll just remind you that it's convergent in this case because r would be equal to 1/3. So what we can notice is that each term of our original series, which we'll now call a sub n, is less than each term of our new series, which we will refer to as that formula as b sub n, for any n greater than or equal to 1. So therefore, by the direct comparison test, this series converges. We know, and let me be more clear how I say that, we know that this series converges, and every term of this series is less than our geometric series 1 over 3 to the n. Therefore, the series 1 over 2 plus 3 to the n converges as well by the direct comparison test. All right, let's look at another example. I'm going to work this one out a little bit more manually here. It says determine the convergence or divergence of this one. So if we look at this one, in fact, actually the very first thing I'm going to make a note of is that 7 on the top can be pulled out to the front. So I'm going to write this equals 7, the sum, and I'm just going to write infinity up here, of 1 over 1 plus n. And instead of writing it as the cubic root of n squared, I'm going to write that to the 2/3. Okay? So this series that I just wrote in red kind of poorly is exactly the same one as our original one. Now we'll note that you might be tempted to say, oh, okay, I got it, Mr. Arnold. Let's compare it, direct compare it to 1 over n to the 2/3, which we know is a divergent series because this is a p series with p less than 1. However, we have a problem here. If we were to take our calculator, if you will, and start comparing term by term, each of the n's, so n equals 1, n equals 2, n equals 3, and adding all of those things together, you will see that it doesn't work, and I'll explain that more now. So what I'm going to say is I'm actually not going to use this one. What I am going to use is I'm going to use this series here, which is the divergent harmonic series. So we know that this is the harmonic series, and we know that it diverges. Now what I want you to realize is this. When I use my calculator now and I start comparing term by term, the first term of this series is 1, and the first term of this series is 1/2. Let me make sure I plug that in here correctly. Yes, good. All right. And then as we keep going, and I just hit equal sign, what you're going to find is the following. You are going to find, so I'm going to let my a sub n be equal to 1 over n, and I'm going to let my b sub n be equal to 1 over 1 plus n to the 2/3. And, oops, let me make a division bar here, and let's go ahead and make a blue less than symbol here. We're going to get this is less than this for all b greater, or not b, all n greater than or equal to, I think it's 4. Let me double check with my calculator. Yes. So when when n is 1, this is not true. When n is 2, this is not true. When n is 3, it is not true. But once you hit n equals 4, after that point, all of these terms, the a sub n will be less than the b sub n. So this is an interesting thing. Now, we know that this series diverges, and we know that it is less than b sub n for all n greater than or equal to 3, or to greater than or equal to 4. So therefore, so I'm going to put dot, dot, dot. It's kind of hard to actually make dots with this. Therefore, we can say that the sum of 7 over 1 plus 3 cubic root of n squared diverges by the, what do we call this? Oh, yeah, direct comparison test. And that's how you'll see me abbreviate it a lot. Okay, so basically what we, and by the way, let me just let you know, if we know that, get rid of this 7, if we know that this series diverges, then if I take 7 times it, it's obviously going to diverge too. So that, there you go. Okay, so there are 2 examples of the direct comparison test. First example was a little bit cleaner. And then this second example here was a little bit trickier. So let's go ahead and move on to the limit comparison test. So the limit comparison test is another comparison test. So what you're going to do is you're going to have your series, and then you're going to have to try to come up with a different series to compare it to, if you will. But this time, instead of doing a direct comparison term by term, we're actually going to compare their limits, or the limit of, you'll see what I mean. So here's what it is. In fact, let's just jump to it. The limit comparison test. I'm going to, what did I just do here? Sorry, I want to change my ink to red here. Okay, good. So the limit comparison test says this. Let each of our terms, a sub n and b sub n, be greater than 0. So this is important. Everything has to be positive, so we can't deal with negatives, okay? If the limit, as n goes to infinity, of the general term of the first series, which we'll say a sub n, divided by the general term for the b series is equal to L, and L is finite and positive, then either both of the series converge or they both diverge. I think this one's a really cool comparison. I think it's one of the best tests. I think it's very interesting. So basically what you're going to do is figure out what your a sub n is and your b sub n is, do the quotient of them, take the limit as n goes to infinity. If that value is finite and positive, then you have either convergence or divergence. Let's see an example. Okay, so first example here, we just want to show that the general harmonic series diverges. So if you recall, the harmonic series, which I actually have already mentioned in this presentation, is 1 over n. So if we actually look at that, the sum of those values, which is 1 and then 1/2, oops, it should be plus 1/3, plus 1/4, and on down the line, that diverges. The general harmonic series, what we're going to do is we're just going to put a positive value a in front of the n and a positive b after it. We want to show that it diverges. Now, we can't use this directly. So what we're going to do is we're going to do a limit comparison test. So what we're going to do is we're going to compare this to this using quotient and limits. So all I'm going to do is I'm going to let this be our a sub n, and then 1 over n is going to be our b sub n. So notice I have, and I'm going to go back to my previous slide. So I've got my a sub n over b sub n, so that's what we have here. So we've got our a sub n on the top, and in our denominator we got our b sub n. We're going to take the limit of this, and it turns out the limit is 1 over a. Now remember, we assumed that a was greater than 0 and positive. Because the limit is greater than 0, because remember, a is positive, so 1 over something positive is positive, we can conclude that this limit, by the limit comparison test, that this series has to diverge. Now let me make sure I say a couple of things here. Consider this a sub n. I hope you realize that that's greater than 0, and I hope you realize that it is also finite. And it has to be finite because the smallest value that a could be is, well, I guess I shouldn't say that. I mean, it could be any real number, but it has to be positive. But let's pick, if it's a really big a value, then it's going to be 1 over a really big value, which is very small but positive. If it's a very small positive value, now it's going to become a big number, but it's going to be a finite amount. So there you go. So that is the other thing I need to mention here. Since this is true, and since we knew this diverges, that was important, then we conclude that diverges by the limit comparison test. All right, last example. Let's do one more here. It says determine if the series converges or diverges. Okay, so this one here, we're going to try to figure out what our a sub n and our b sub n are going to be in this particular example. And in this case here, I think what we're going to do is we'll just let a sub n equal the square root of n over n squared plus 1. And we'll just leave it as that. Now let's try to figure out what b sub n is. So here's what I'm going to do for b sub n. For b sub n, I'm going to say that the top is, well, I'm going to say it's still n to the 1/2. But the denominator, instead of saying it's n squared plus 1, I'm just going to make it n squared. So this is now going to be able to be reduced to 1 over n to the, and that'd be 3/2. Okay? So now that I have that, now what can I do? Well, here's where we're going to do our limit comparison test. We're going to do the limit as n goes to infinity of, let's do the top thing. So that's going to be I'm going to write that as into the 1/2 over n squared plus 1. All of that divided by, and then the bottom I'll do that one in, let's say, I guess I should have done that one in red, but whatever. 1 over n to the 3/2. And we just need to figure out what this limit's going to be. So when you divide fractions, you multiply by the reciprocal. So this is going to be the limit as n goes to infinity of, and then this is going to be n to the 1/2 over n squared plus 1. And then we're going to multiply this by n to the 3/2, essentially, if you will. Okay. And now what we're going to try to do is figure out what that limit's going to be. Well, we can just simply multiply across, so that's going to become n squared in the numerator. I'm kind of running out of room here. I'm going to try to squeeze this in here. So this is going to be the limit as n goes to infinity. I'm going to move my head up here. And let's see here. Now we're going to have n squared. Oops. There we go. N squared over n squared plus 1. And now we can play that trick where we divide the top and the bottom by n squared. And so therefore this limit's going to be equal to 1. 1 is clearly finite and positive, so that's greater than 0, and it's finite. So now we can draw our conclusion, and our conclusion should be this. In fact, let's put this all together. Remember, I was doing a limit comparison with this. In other words, we were talking about the series 1 over n to the 3/2, right? So that is a convergent p-series, right? Oops, convergent. That's a V. I keep thinking congruent from my geometry class. Sorry. That's a convergent p-series. Since that is a convergent p-series, I can conclude, this is my final answer now, this series converges by the limit comparison test. And there you go. All right, so that will be that, and thank you for your attention.